Here we have an alternative formula for the cross product, which is going to turn out to be pretty important in terms of insight about this normal vector n, which is equal to b crossed with c. Okay, so our exercise is to prove that b cross c squared, the length of b cross c squared rather, is equal to the length of b squared times the length of c squared minus, b dot c squared, which is pretty quickly and obviously equivalent to the length of b cross c is equal to the length of b times the length of c times the absolute value of sine of theta, where theta is the angle between b and c in the plane represented, or the plane spanned by b and c. Moreover, taking a look at this length of b times length of c times sine of theta, we see that this, let's see if I can draw this correctly, this would actually give the area of the parallelogram that has b and c as its base vectors. And it's fairly easy to see how. If we drop a line from the end of C that meets the vector b at right angles inside this plane, then clearly this value h, which is the length of this dotted line, is equal to the length of c times sine of theta. And so that means that the area of the parallelogram is the length of b times h, which is the length of b times the length of c times sine of theta. So that tells us that not only is this normal vector n equal to b cross c orthogonal to b and c, and therefore the entire plane spanned by b and c, we have that the length of this vector n equals b cross c is the same as the area of the parallelogram with base vectors b and c. So that's really interesting. And so an alternative way to write b cross c is the length of b times the length of c times sine of theta times u, where u is a unit vector that is perpendicular to both b and c in the pictured direction. In other words, u is, the unit vector of the unit vector in the same direction as b cross c. And we got a little picture down here called the right hand rule. So you curl your fingers around like this, and when we curl the fingers, it should go from, I'll just draw a picture here. So we're curling our fingers around, and when we curl them, it should go from b to c in that direction. And then the thumb points upwards. That's going to be the same as the direction of our normal vector n equals b cross c. So if we have our normal vector pointing in this direction, that means we must have our vector b something like this, and then the c something like that, so that the fingers curl around, they go through b first, and then they go through c. Alright, we're pretty much done with this slide. All that we've really got to do is actually prove the result. So let's go ahead and do that. First of all, let's suppose this is true and then get to here. We know that the length of b squared times the length of c squared minus b dot c squared, so that's equal to the length of b squared, the length of c squared minus, and then the dot product b dot c is the length of b times the length of c times cosine of theta. So this is going to be the length of b squared times the length of c squared times cosine squared of theta. And then we can factor out the length of b squared, the length of c squared. So this is equal to the length of b squared times the length of c squared times 1 minus cosine squared of theta, which is clearly sine squared of theta. And then if you take the square root of both sides of this, remember this is equal to b cross c modulus, or length, squared. And so if you take square roots of both sides of that equation, you end up with this. So all that's left to do is prove this part in the blue box. So let's go ahead and do that. So first of all, let's say that B is equal to B1, B2, B3, and C is equal to C1, C2, C3. Then we have B crossed with C is equal to B2, C3 minus C2, B3. And then it's going to be, we delete the middle one, and we go in the opposite order, so C1, B3 minus B1, C3. And then lastly, B1, C2 minus B2, C1. Okay, now we're ready to go, so let's go ahead and calculate the length of B cross C squared. So the length of B cross C squared, it's going to be B2 C3 minus C2 B3 squared plus C1 B3 minus B1 C3 squared plus B1 C2 minus B2 C1 squared. Meanwhile, let's look at what we have on the other side. So B, the length of B squared times the length of C squared minus B dot C squared. Alright, so this is equal to B1 squared plus B2 squared plus B3 squared times by C1 squared plus C2 squared plus C3 squared minus B1 C1 plus B2 C2 plus B3 C3 all squared. To save ourselves a bit of work, we can quickly observe that we're going to get some cancellations, and so there are some terms that we don't need to write out. For example, B1 squared C1 squared is going to cancel out with B1 C1 squared, and so we don't need to write any of the BI squared times CI squared. So we can just focus on, say, the other two. So B1 squared C2 squared plus B1 squared C3 squared plus B2 squared C1 squared, and then we don't have B2 and C2 because it's going to be cancelled out here. So B2 squared C3 squared, and then plus B3 squared C1 squared plus B3 squared C2 squared. Okay, and then out of this thing here, we're going to be doing all the other terms except for the ones multiplied by themselves. So, and there's actually going to be 2 of each one. So minus 2 times B1, B2, C1, C2 plus B1, B1, B3, I guess, keep it in that order, C1, C3, and then plus B2, C2, B3, C3. So B2, B3, C2, C3. Okay, and now the question is, does this thing here, this last green line, look like this blue line? And thankfully the answer is yes. We just have to group them in the right way, because we got minus 2 sets of 4 terms in the middle, and everything else that we would like squared is squared. For example, we can immediately eliminate, so this B2, C3, and C2, B3, wherever that is, that'll be over here. And then we just need a product of B2, C3, B3, C2. So me writing it in my complicated order was actually made things harder. B2, C3, B3, C2. Alright, so all together these three would cancel with this here if we were to set them equal to one another. Rather than cross things out, I'll just underline them to show what goes with what. Alright, and then next up we've got this, the only problem is I'm going to run out of colors. Okay, C1, B3 minus B1, C3. So C1, B3, and then B1, C3. And then we just need B1, B3, C1, C3, which is here. Nice. And last but not least, B1, C2 minus B2, C1 is clearly these three. And so we are done. So that's an alternative formula for the cross product, which also tells us that the length of our normal vector n equals b cross c is the same as the area of the parallelogram, which has b and c as its base vectors.